Hey guys, we're going to take a look at scatter plots today and basically kind of review what you would have learned last year about scatter plots in the sense of trends and things that you can see in them. And then we're going to look at how to determine correlation and causation from statistical information that's given to us. And so the scatter plot part of this, for the most part, will be review. The correlation, causation stuff will be a little bit new. So you want to pay attention especially to that part. Hopefully the stuff on scatter plots is something that's kind of familiar to you already. So by the end of this, you'll be able to identify trends in scatter plots. And it says use Desmos, but we're actually going to use the T84 because I've decided that's easier for y'all than remembering how to type it in Desmos. To determine the line of best fit and the correlation coefficient. And I know that in 8th grade you do lines of fit. We're going to look at a different way to do that now that we have access to the T84. And then correlation coefficient will be brand new to you if you've not seen correlation coefficients prior to this year for algebra. So let's get into this. So we know that scatter plots represent data on a coordinate plane. They're a collection of points that don't necessarily form a line. So we're talking about the scatter plot when we're talking about you've got your XY coordinate plane, and then typically you've got a bunch of data points that have been plotted on there, but because it's data and it's not perfectly linear situations or whatever, you create something like a scatter plot instead of having set points that all fall in a nice, beautiful, perfect line. And so that's an example of a scatter plot. The purpose of the scatter plot is to be able to look for trends within the data, so to be able to see overall what does the big picture of this data look like is happening, what's the relationship between the X and the Y based on the data that you get. So from the look of it, you should be able to identify correlation and association. I'm spelling that wrong. Yeah, I know I'm a math teacher. Of the data that's described. So the appearance, the shape of the graph, the appearance of the scatter plot can tell us about the correlation of the data. What kind of association does it have? Does it have like a positive association, a negative association? Is there a linear correlation to what we see? Things like that. That's what we're looking for when we talk about looking at the shape and the appearance of the scatter plot. So some specific things we want to be able to describe about scatter plots are things like whether they're strong or weak, whether they're positive or negative, whether they're linear, nonlinear, whatever. And so on the next slide, we're going to look at some of those up close. So linear indicates the shape of the scatter plot is a straight line. Now, it doesn't have to be perfectly straight, but if overall the data is trending in a line, the situation of a straight line, or an overall the same direction without a curve in it, then we're talking about a linear situation. Nonlinear would describe something that's curved. And then no correlation at all would be stuff that's just random. So I actually messed up here and didn't put an example of anything that's nonlinear, but just to kind of give you an idea of what something like that might look like, that would be the situation of if you've got like a situation like this, where your data is obviously trending in a particular direction, but it's a curve, not a straight line that it's trending in. That indicates a nonlinear situation. But all these others are either linear or have no correlation at all. If you notice in one like C, very obviously trending in a straight line, right? A is also trending in a straight line. E is trending down, but in a straight line. So we've got these linear associations in A, C, and E. Now, B, D, and F are a little more spread out, a little more randomized, But overall, with D, we can see that the data is generally trending upward. In F, the data is generally trending downward. So those technically are also linear, even though the data is a little more spread out. But now B, you can't make heads or tails of what B is doing. It's not going up, not going down. It's really just all over the place over here. So B would be our example of no correlation. All of these others would be examples of linear. So linear would be things like A, C, D, E, F. Nonlinear would be examples like B. And then this would be a good example of, no correlation would be B. And then nonlinear would be an example like the one I drew over there. Now, other things we want to be able to describe are things like positive or negative. This works the same way slope does. So something with a positive slope is something that's going to be rising as it goes from left to right. As far as correlation is concerned, that means as one goes up, one variable goes up, the other variable goes up also. So you have the same direction of change happening between both. So when one goes up, the other also goes up. Negative association would be an overall downward trend, where if one variable goes up, the other variable is coming down. So usually as the x gets bigger, the y is going to be getting smaller in that situation. So when we look at these graphs over here, again, we look at it just like we look at slope. So these positive ones are the ones that, as you read them from left to right, are going upward. Hopefully you look at that and you can see that A, C, and D all have an overall upward trend. Because if I were to start on the left side and go to the right, overall we would be going up in a positive direction. E and F both have a downward trend, which makes those negative. And then again, B has no real association, so B is just kind of there. And then the last thing we look at is strong or weak, and that relates to how close to the line the dots are. So strong would be a situation where the dots are very close to the line. Weak would be a situation where they're more spread out. And so it's kind of hard to be able to say, well, hey, this is strong and that's weak just by looking at different ones. But it should be a situation that we can rank these in order from the strongest to the weakest based on how close together those dots actually are. So if I'm thinking about that, looking at this situation, so I'm going to go strong. So strongest to weakest. Looking at this data, the one that is the closest to a perfect line, the one that the dots are as close together as possible on the line of fit that I've drawn, or the trend line that I've drawn through this, would be C. So C has the strongest association because its points are closest to the line. Hopefully, if you're looking at the rest of that and looking for the next strongest, A appears to be maybe the closest to the next, followed by E, because those are all very close to the line. Now, we talked earlier about how B, D, and F have spread out more. Obviously, B is going to be our weakest because there's really no association there at all. But we need to figure out where D and F would fall. They're very close, in my opinion. I'm going to say D is maybe just a little bit closer to the line than F is, but not by much, if at all. So we'll put it like that. If you think F should go before D, that's okay. It's close enough. But you should be able to look at those and rank them overall from strongest to weakest based on the appearance of the dots that are there. Okay, let's keep going. Okay, so the next thing we need to look at are correlation coefficients. Correlation coefficients are a number value that is assigned to a linear model to basically tell you how well that set of data fits the model. So that correlation coefficient is always going to be a number that falls between 0 and 1. Or it could also fall between 0 and -1. They can be negative if the overall trend of the data is negative. The negative doesn't affect how strong or weak the data is. It just affects whether the number is going to be positive or negative because the trend in the data is positive or negative. So we'll do something called a linear regression model in a minute. And in that linear regression model, the letter R represents the correlation coefficient. So you'll want to be familiar with that if you're doing a regression model to figure out a correlation coefficient. The R is the value that you look for with that. So generally speaking, when you look at a correlation coefficient, the data is considered to have a weak association or weak correlation when that correlation coefficient falls between 0 and about 0.5. Now again, that can be positive or negative 0.5. And then you consider it to be strong if that number is between 0.5 and 1. So basically, the closer a number gets to 1 or negative 1, the stronger that correlation is. The closer it is to 0, the weaker the correlation is. So if you're looking at a comparison of correlation coefficients, or you're looking at a correlation coefficient and wanting to use it to describe your data, then a correlation coefficient of negative 0.26 would be considered weak because it falls between 0 and 0.5. A correlation coefficient of something like 0.75 would be considered strong because it's very close to 1. Same deal if I had like negative 0.85 would be strong because it's very close to 1 or very close to negative 1, whereas something like 0.17 would be weak because it's very close to 0. So when we're looking at trying to determine whether a relationship is strong or weak, that correlation coefficient will tell you one way or the other how that's going to work. So let's look at some examples of correlation coefficients. These are the same scatter plots that we used on the last problems. But now we're going to see if we can match up the correlation coefficients with the scatter plot that would be best suited for it. So if you remember earlier when we were ranking these scatter plots in order of strength from the strongest to the weakest, and we said that C would be the strongest scatter plot that we had in the set. So when I go and look at these correlation coefficient options, because I have 6 different numbers here that represent correlation coefficients, 0.5, 0, 0.85, 0.92, 1, 0.48. Those are negative, by the way. Then I'm looking for the closest that I can get to 1 would be the strongest. The closer I am to 0 would be the weakest. So if C is my strongest, and I look at these numbers and I have a number that is at 1, well, that's going to be considered perfectly linear, which is basically what C is. So C is going to match up best with a correlation coefficient of 1. Now, with the same reasoning, if I know B was my weakest and 0 is the closest to 0 we get, then an R value of 0 has to match up with B. Now, the rest of these I'm going to put in order based on strength and based on whether they're positive or negative. So you'll notice that we have a negative correlation coefficient here and here. We have positive correlation coefficients here and here. So when I look at my data, I know that A and D are both positive, and I know that E and F are both negative. So I'm going to match up A and D with those 2 positive correlation coefficients. I'm going to match up E and F with those 2 negative correlation coefficients. So between A and D, A is stronger. Between my 2 positive correlation coefficients, 0.92 is stronger than 0.5. So A is going to match with the 0.92, D is going to match with the 0.50. And then I'm going to do the same thing with my 2 negative ones. Again, the negative doesn't change how strong or weak it is. So the number itself being close to 1 tells us which one's the strongest. So E is the strongest graph. 0.85 is the strongest correlation coefficient. So E will match up there, which means F is going to match up at negative 0.48. And if you remember when we were sorting these earlier, we said that we couldn't really tell between D and F which one was stronger. We thought D maybe was a little bit stronger than F. When looking at our correlation coefficients, 0.5 and 0.48 are very, very close together. So it really makes sense to us that those would have been pretty hard to tell which one was stronger based on what we see. All right, so let's keep going with this. So we can also do something called a linear regression model, or creating a line of best fit with scatter plots. Now, you would have done this in 8th grade. If you remember doing a scatter plot like this, and again, don't draw this, just think for a minute. You had a scatter plot, and if you remember back in those days, so far ago, last year, you had a scatter plot like this, and you would have had to look at that scatter plot and try to draw a line through those points that was as close to the points as you could get it, and evenly split the data above and below the line. This program that I used to do this doesn't auto fix a line, so I'm actually going to undo what I just did and see if I can find a line tool instead. Oh yeah, here we go. Let's use that. Maybe. Okay, so I'll draw a line through the data. That's better. And we try to evenly split it and make it follow the trend as best we can. Again, may not be perfect, and that's okay if it's not. It's kind of like this. So that's about where my line of fit would fall. And then I would take that, again, back in 8th grade, and try to find 2 points that existed on the line that I knew the exact value of, stop sign point type deal. And then I would use rise and run to figure out a slope and a y-intercept for that. And it was all an estimate based on about where we felt like those things would hit. And so we were estimating those lines of fit, using those lines of fit to make predictions, that kind of thing. And that works. It's not going to give you a perfect prediction, but it does work. But for algebra, we're no longer going to do that by hand. We're no longer going to estimate about where we think it would fall. We're instead going to use a linear regression model to calculate what would be the best fit line for the data, meaning the one that is as close to all the points as you can get it, and evenly splits the data above and below it. So we're going to determine a best fit line to represent the data. That's a line drawn through the scatter plot, evenly splitting the data and remaining as close to all the points as possible. Sometimes they'll call that a best fit line. Sometimes they'll call that a linear regression model. So you could see both of those things. But instead of estimating it, we're going to calculate it using the TI-84. So let's look at how we do that. So the TI-84 can determine the line for the best fit model using the linear regression option that is in STAT. So just like we did the other day when we were doing one variable statistics, looking at our mean and our median and our quartiles and our maximum, minimum, that kind of thing, we're going to go into STAT and we're going to put our table of values in for L1 and L2 this time. So we're going to have an X and a Y table. And we're going to put the X's in for L1 and we're going to put the Y's in for L2. So I'm just going to make up some numbers. Let's pretend like we've got a set of numbers 0, 1, 3, 5, 6, and 12, 15, 19, 18, 20. So let's just say that was our data. And so in your calculator, if you got a calculator with you, go ahead and pull up STAT. I'm going to go grab one. Hang on. Pull up STAT, go to Edit, and then you're going to put in the L1 and the L2 values in your list. I don't think there's a way. Let me play around with this for a minute. I don't think there's a way for me to show this to you on the screen here, so we just have to go by words. But you're in STAT. You should know how to do that because you were here the other day. You're in the edit list, you're on L1, you're typing in that list, 0, 1, 3, 5, 6. Then you're going to go over to L2 and type in 12, 15, 19, 18, 20. So here's what's important to you, a couple of things. Number one, you have to make sure that the points line up when you do this. So before it didn't really matter what order you put the numbers in when you're just putting them all in L1. Now you have to make sure that 0 and 12 are aligned with each other, that 1 and 15 are aligned with each other, and so on. If you don't do that, then you're going to end up with a different model than what's expected. So we put those things in. Another thing you need to check for, and make yourself a side note of this, you have to make sure Stat Diagnostics is turned on. And I'll tell you how to find that. Because when you reset your calculator, it automatically turns that off. And that's the way that we get our calculator to show us the linear, or the R value, the correlation coefficient. So go ahead and load that in STAT. Hit the mode button, which is the button next to your second key. scroll down or look down until you see the word Stat Diagnostics and make sure that it's toggled on. If it's got off highlighted, then you need to move over to on, press enter, and then you can exit back out of the mode thing by either pressing clear or just press stat again to go back to your list. So once you make sure Stat Diagnostics is on, go to your calculate menu, and you're going to go to the fourth option this time. It says Lin Reg AX plus B. And you're going to press enter, go down to the word calculate, press enter again. And it's going to give you 4 pieces of information. It gives you an A, a B, an R squared, and an R. The things that are important to us are going to be the R, the A, and the B. So R represents the correlation coefficient. So if a problem tells you to find the correlation coefficient, you're going to be giving the R value for that. So for the data set that we just put in, my calculator says the R value is 0.89931677788. We usually round that to about 2 digits. So 0.899 would round to probably 0.90, right? Something about like that. I'll be honest with you, they're not going to give you a question where they ask you to give the correlation coefficient and they tell you to round it to the nearest hundredth, and one of the options is 0.89 and one of them is 0.90. They're just not going to give you that. So as long as you get pretty close and know what number you're looking for, you're good. R squared just represents the squared correlation coefficient. It's not important to us, so we're not really worried about it, but that's what it is. It's the squared correlation coefficient. And then the A and the B represent the parts of the linear equation that would be the line of best fit for this. A represents a slope. Yes, I know that slope is usually represented by M. I don't know why the TA84 decides to do it with A. That's their business, whatever. It does tell you up there above it y equals AX plus B, so you can remember which way that works. Like the A goes with the X and the B is behind it. But B represents the y-intercept for that equation. And so if I want to write the equation for the line of best fit for this with a slope of 1.15, is what mine tells me, and a B value of 13.34, I can put those two things together into an equation of 1.15x plus 13.34. And that represents the equation for the best fit line or the linear regression model for this set of data over here. So questions could ask you about getting this. Questions could ask you for this value. You want to make sure you know what those different pieces represent so that you can give whatever part of that they're asking you for. Now this we'll use in our next lesson to make predictions with the scatter plot. Using this line of best fit as a guide for about where the data should fall or could be estimated to fall based on where that line of fit exists. So we'll be using these kinds of equations quite a bit. You want to make sure you're able to find and create that as you need it. All right. So we're going to do an example of this. So the first thing they ask us to do is determine if there's correlation between the data in the set. If so, describe it. Write its correlation coefficient and a linear regression equation to model it. So I'm going to go back to stat, go back to edit. I'm going to clear my list out. Remember, you go up to L1, hit clear, go up to L2, hit clear. And then we're going to start this again. 1, 4, 5, 7, 9. Notice that the table this time goes horizontally, but these are all X's. So all those have to go in the L1 list. All these go together in the L2 list. So make sure that even though the table looks horizontal here, you're putting it in vertically in your calculator. So 1, 4, 5, 7, 9, 14, 34, 27, 40, 38. Again, once you get it loaded, go to Calc, go to option 4 for linear regression. And we're going to first describe the correlation coefficient. That's our R value. So according to my calculator, my R value is 0.872291082. So we're going to call that about 0.87. Now, from that, I know two things. I know that there's a positive relationship because that value is positive. And I know that the relationship is strong because that value is larger than 0.5. So I'm describing the correlation between the data in the set using that correlation coefficient to tell me what it is. Then I'm going to write the equation for the regression model. And so I'm going to get that equation using the A and the B. According to my calculator, the A value is 3.027173913. I'm only going to round it to about 2 digits. So I'm going to say 3.03x plus, now I'm going to give the B value. Again, according to the calculator, the B value is 14.85869565. So I'm going to round that to 2 places. 858 would round up to 86, so 14.86. This will be the linear regression model that fits that set of data. All right. Okay, let's do another one. Same thing. Go back into Stat, go to Edit, clear your list out, put this list in. Okay, so I put my list in, gone to Stat. If you're still working on it and I'm moving too fast for you, just pause the video until you catch up so you can be where we're at the same time. So again, I'm going to look at my R value first. I'm actually going to put this down here because I got more room to write. So look at my R value first. According to my calculator, my R value is negative 0.93956. So I'm going to call it about negative 0.94. What that tells me about our relationship is that it's negative, because that number was negative, and that it's strong, because that number is larger than 0.5. So then to write the equation for our line of fit, our linear regression model, the A value was negative 0.0964353915. We'll call that negative 0.10. And if you're wondering about that, if you're looking at negative 0.096, and I want to round to 2 digits, that 6 behind there tells me that 9 has to bump up to a 10, which is why that rounds to negative 0.10x, or 1/10 x, plus the B value is 15.25. So this would be the line of fit. The R value would be our correlation coefficient. Again, we can use that to tell that this data has a strong negative relationship. Okay. So take just a minute, pause the video right here, and go and see if you can find an R value and a line of fit for both of these sets of data, and use the R value to describe whether the relationship is positive, negative, strong, or weak, based on what that R value comes out to be. When you get done, unpause the video and you can check and see if you were correct. Okay, take a look at what I got here for both of these. And if you got something different, go back and check your data set. Because really the only way to mess this up, other than maybe you rounded incorrectly, would be to have put the wrong data set in to start with. So you want to be real careful with what you're putting in, because the calculator is going to calculate it correctly every time. As long as you put the right data in, it'll be able to generate the correct thing back out for you. All right, if you got that right, then we'll roll on to the next thing. So the next thing we want to look at is the idea of correlation versus causation. Correlation refers to how data fits a linear relationship. Meaning, does it fit where one goes up, the other goes up? Does it fit where as one goes up, the other comes down? This would be our positive correlation. This would be our negative correlation. Causation refers to whether the x variable caused the y variable to change. Big thing we want to note is that being correlated does not automatically imply causation exists in a situation. So two things can be related, but one not actually cause the other to change. So thinking about some examples of what that might look like. Would be a situation of, you might see that a person who goes to a lot of piano concerts, piano recitals, also attends a lot of symphony performances because maybe they like classical music, right? So they go to both. But just because you go to a piano recital doesn't cause you to go to a symphony performance. There's no causation there. Might be correlation because as one goes up, the other also goes up for people, but there's not going to be causation in that situation. Causation means one has to cause the other. So by the same example, I have this example here about going to the movies and renting movies. So a person who enjoys going to the movies more often might be associated with a person who rents movies at home more often, or might be a person who rents movies at home more often. There's probably a positive association there because someone who goes to the movies is a person who likes movies, and someone who rents movies at home is a person who likes movies. So if you enjoy going to the movies, you probably also enjoy renting movies at home because you're a movie person. But going to the movies does not cause you to rent movies at home. Okay? So there's not going to be a causation situation here. There may be correlation, but not causation. However, going to the movies more often can cause you to spend more money because going to the movies costs money, right? If you go to the movies, you're going to have to spend money in order to get into the movie, and if you are hungry and want snacks, you have to spend money on that. So this has causation because going to the movies causes you to spend the money. So there's causation here. So this is both. You can't have correlation without causation. I mean, you can't have causation without correlation. This is correlation only. Now, it is possible to have a situation where there's not even correlation. For example, if you had data on a person's gender and their ability to read. I'm not making that up. A person's gender is not affecting their ability to read. So the data that you get on that is going to be not related at all. There's going to be no correlation at all in that because they're just not related points. But a situation where a movie person might rent movies at home and go to the movies would be a correlation situation because those could be related, but not causation because renting does not cause them, or going to the movies does not cause them to rent movies more often. Okay. So looking at some examples of this. A says, riding a bicycle more often is associated with stronger leg muscles. So it tells us that the more you ride a bike, the stronger your leg muscles are. That's correlation. As one goes up, the other's going up. Does riding the bike cause the stronger leg muscles? It does, because riding a bike is exercise, and it will strengthen your leg muscles when you do it. So this is correlation with causation. Okay, so this is correlation and causation, or you can call it both. B says having quicker reaction time is associated with being able to run more quickly. So they tell me that they're related. It's associated with that. So I know there's correlation here. Does reacting faster cause you to run more quickly? It does not. Some people are fast runners because of the way their bodies are designed. Some people are fast runners because of strategies and things that they use. But a quicker reaction time does not make you or cause you to be a fast runner. So this one is correlation only. And then C says wearing a football jersey more often is associated with throwing a football more often. So again, it tells me that as one goes up, the other goes up. This is correlation. But then we have to decide, does wearing the jersey cause them to throw the football more? It's an interesting question. Would wearing a jersey cause you to throw a football more? Well, it does, because the ones who are wearing the jersey are likely to be ones that are on the team. Now, there are other people who could also be wearing jerseys that are not throwing the football as often. But one of the reasons that we see such a correlation between these data points would be that the ones that are on the team are wearing the jerseys and doing the throwing of the football. So this is correlation with causation. So take a couple minutes and take a look at these and decide what you think. They're all going to be correlation, but decide if they also have causation in them. And write out beside each one whether you think it's correlation or both correlation and causation. You cannot have causation without correlation, so that's not going to be a thing. When you get done answering those four, come back, pause the video to answer them, then come back and see if your answers were correct. Okay, so when you looked at those, hopefully you got correlation only for the first one, and then the last three were both. And here's why. With the first one, pruning more fruit trees does not cause you to own more varieties of fruit trees. You could prune 400 peach trees, and that doesn't mean you're suddenly going to own apple trees, right? There's no causation in that. So that's correlation only. The second one, drinking hot cocoa is associated with washing mugs more often. Well, there is causation there, because the more hot cocoa you drink, or the more often you drink hot cocoa, the more often you're going to have to wash a mug, because you're drinking hot cocoa from a mug. The third one, using a fireplace, is associated with burning wood or gas more often. If you're using a fireplace, you have to use some sort of fuel. Might be a wood fireplace, might be a gas fireplace. But because you must have fuel in order to burn a fireplace, or to use the fireplace, that would also be causation. Using the fireplace causes you to burn wood or gas. And then swimming more often is associated with more muscular shoulders. Swimming causes an arm workout. Swimming causes you to be more muscular in your shoulder area, because it's exercise in that specific area. And so that would be considered causation as well. So moving on, let's look at how this might be tested. And so we'll look at several different test prep type questions, and I'll let y'all work a few of these on your own, and then we'll kind of come back together and talk about them. But look at this first one. So they have a scatter plot, they have a line of fit drawn through it, and they have the question of, what does the slope of the data imply? And so remember, the slope is that rate of change, that A value. Hopefully you look at that and you, number one, notice that it's positive, which means as one thing is going up, the other is also going up. Specifically for this, it's as the surface gravity increases, escape velocity is also going to increase. So when we look at what the slope tells us about the data, A says the greater the surface gravity, the greater the escape velocity. Well, that makes sense. As this goes up, this is also going up. That's what's allowing that line to trend upward. So A is probably good. We can check B and C and D just to make sure. B says the greater the surface gravity, the smaller the escape velocity. Well, that's not true, because as this gets bigger, this value is also getting bigger. So B is out. C says the surface gravity is equal to the escape velocity. It's not. I'm at 0.2 here when I'm at like 2.2 here. That's not the same. And then D says the surface gravity is 10 times the escape velocity. And that may feel true in some areas. Well, 0.2 and 2 would be 10 times, so that's actually falling under. This is falling under. So that doesn't quite hold true anyway. Plus it says surface gravity is 10 times escape velocity. That would mean this is 10 times this, which is definitely not true. So those, all three are out, and A is really the only choice here that makes sense. All right, take a look at this. They say, it gives a table of values, and it says, based on the correlation coefficient, which characteristic describes the relationship between the hours since the park opened and the number of people who entered the park? So take a minute, go find your correlation coefficient for this problem, and then make a decision about what you think the correlation tells you about that data based on what you get there. Pause the video, do that, come back and see if you were right. Okay, for this one, you should have gotten an R value of 0.99, which indicates a positive and strong correlation for that data. Again, that R value comes from putting these in stat, going to calculate, going to the fourth option, len reg, calculating that value from there. So take a few minutes. There are a few questions left. I think there are maybe 5 or 6 questions left in these slides. If you'll go through the rest of these test preps, answer each one, and then come back and see if your answer was correct on them. Then we'll kind of roll through the rest of these real quick. So pause the video, answer each one, and then come back and we'll take a look at what you got. Okay, so when you looked at this first one, that negative 0.29 indicated a weak and negative correlation. Negative because it was a negative 0.29, weak because it was smaller than 0.5. For the next one, they asked for the strongest linear model, so hopefully you pick negative 0.98. If it had said something like the strongest positive linear model, you would want to pick 0.84. But because it didn't care if it was positive or negative, negative 0.98 would be the strongest because it's the closest to 1. Remember, the negative doesn't affect its strength. It just affects the direction that it's traveling. All right, next. The correlation between this was positive, so hopefully you picked B. And we know that because it's rising from left to right. For this one, they asked for a positive correlation and causation. So you were looking for the one where it's one went up, the other went up, and causation occurred. The only one that does that is D. So as attendance increases, ticket sales also increase. That's positive correlation. And it's causation because when you go to a concert, you have to buy a ticket. So going to a concert causes you to purchase the ticket. That's a causation situation. The only other one that had a positive correlation was B, where as you order milkshakes, the basketball game score increases, which just sounds ridiculous. But anyway, there is a positive correlation because the one goes up, the other goes up. But it's no way causation because ordering milkshakes does not cause the basketball game score to increase. Be interesting if it could, but it doesn't. All right. This one asked which of these variables were related by causation, meaning one causes the other to change. The only one that is purely causation is B, the amount of exercise and the calories you burn. Some people like to argue about age and weight. That's only true to a point. Once you reach a certain age and your body is full grown, your age no longer directly affects what you weigh. Other things in your lifestyle would affect that. Same thing with height and shoe size. There are plenty of people who are tall with big feet and plenty of people who are tall with small feet. And so there's no causation that exists within that category either. And then the last one, you're going to probably see a question like this on state tests. They love these kinds of questions. Most important thing for you to recognize is that correlation doesn't mean there's going to be causation. So when you read your answer choices on one like this, always pick the answer that says something like correlation does not imply causation, or correlation does not mean there's always going to be causation, because it doesn't. You could have correlation with no causation at all. Okay, and that wraps up that lesson. So if you are finished, if you'll make sure you submit those, and then you are ready to move on to the practice. Y'all have a great day.